All right, let's get started. So first lecture after the midterm, thanks for coming back. The midterm solution sets have been online. I have all of I have like an Excel spreadsheet with just your last four digits of your ASU ID with all of whether you got the question correct or not, as well as which answers you submitted. So I'll end up posting that. I had some formatting issues that I ended up coming into the end of the day yesterday, so I didn't get a chance to post it yesterday, but I should be able to post it today. So you should have all your scores are already in Canvas, but you should then get that breakdown. You'll actually be able to see how well everyone did on each question and how you kind of compared everybody, as well as what the right answers were for each question, which are also in the solution sets, as well as what your answers were. So hopefully that will help, because we've got this retake, which will be a week from today. It is a different exam than the midterm. It is 31 questions, just like the midterm was, but each question is unique. It's not just a reshuffling of answers from this one. So it's designed to be very, very similar. So I think it's equal in difficulty, and if you did well on one, you will do well on the other for sure. But they are different. So if you come to the retake, don't expect the questions to be identical, and you just have to, remember what you selected on the first one and then find it on the second one, because they were different questions. They're just over very similar content. And then the course grade, your midterm grade will be whatever the highest of these two are. So if you're happy, so I think the scores, the range, I think the lowest score was like a 12 out of 31, whatever that is in percent. So, I don't know, I guess that's a little, maybe 40% or something, or 30%. And then the highest was a 30 out of 31. And the average was, I think, like I posted on Canvas, 72 or 73%. So I was relatively happy with a 73% average and sort of a spread around that. So and there's opportunities to improve that. And so that's what the retake is there for. Then the lab schedule, I know some people are wondering about this. So fall break, which is next week, there's technically no lab scheduled. So these labs have been online anyway, but that just means at the end of fall break week, there won't be a lab due. So the next lab week, the next sort of active lab week, is the week after, the first full week after fall break, and that's when Lab 8 hits. And Lab 8, again, will be available online as well. And this is where we'll actually get into input model, the input analyzer, which we'll start to talk about in these lectures. And this will be a tool that you'll use a lot in your final project, especially in the first deliverable for your final project. And so that's how Lab 8 will kind of be folded into that. And then after you've had practice with that in Lab 8, then the next week, you are going to, by then, you'll already have formed your final project teams. I'll talk about that in a second. And you'll go out and collect some input data on the system you've identified. So, let's say, for example, you identify a Chipotle restaurant or something like that. Well, you might go out and measure data on how the time between arrivals, or how many arrivals occur in every 10-minute period, or how long do particular services take, those sorts of things. And then in this input modeling report, which I'll talk about, you'll use the tools that we've introduced in Lab 8 to start fitting distributions to those so that you can build a stochastic model of that system. So that's going to be that kind of week there. And then after that, we'll have normal labs for the next 2 weeks, Lab 9 and Lab 10. And then after that, those lab periods, there'll be 2 remaining weeks left before you present. And those will basically be open lab times where the TAs can help you with any questions that you have that have cropped up in doing your modeling in Arena. So this is, from here on out, we're basically, prepping you for the input modeling, showing you some more advanced features of Arena that may be useful in your final project, and then giving you time to come in and ask questions if you need that time to develop that final project. So that's kind of the schedule of the labs moving forward. Then final project is what I mentioned here. So all the info of this has been posted online now on Canvas. There's a description, there's an example report. I think this is actually from before I taught the class, they modeled 4 peaks. They used a relatively sophisticated model with a lot of submodules and some routing and things. It's a pretty decent example. So there's that example report will kind of give you an idea of what these things look at. We still use the same format that they used then. And then there's this presentation evaluation form. So when you present, then I'll invite not only the TAs from this class, but I'll invite other grad students and faculty who would like to come and evaluate you. And there's sort of a rubric that they will fill out that you can see, and that's kind of what points you'll get. We'll have the average of those from the people that are watching your presentation. And the presentations will happen in lab. And so I'll sit there all day and watch all of your presentations, but you only watch the presentations for your lab section. But you have to come to your lab section. And you have to watch all of the presentations from your lab section. And so the basic idea is you analyze a real-world system using Arena. You're going to do this all from scratch. You're going to gather the data. You're going to do the input models. You're going to build it out of Arena. The call center example that I think you've seen in Lab 7 is kind of that demo for Lab 7. It was a great example of the type of complexity that would be, if you had something like that, then that would be a perfect, submission for one of these presentations. So more complex than the simple examples we've been doing in the lab, but not too bad. So still contained within the kind of student constraints of the Arena software project. It's a group project. I know a lot of people don't like group projects, and I didn't either. But ABET, ABET wants you to do a certain number of group projects, and ABET wants one of those group projects to be here. So we have to have a group project in this class. It also, because we have these 14, 15-minute presentations, it's just not feasible for everybody to do those separately. We'd spend 2 weeks of presenting. And so, so that's why you have to have these group projects. It's not. I always get nicked on my evaluations because he made us do a group project, and they make me make you. So, so hopefully try to be optimistic, and I think it is a good opportunity to do something that you will do a lot for the rest of your kind of academic or career, or not academic, your industrial career is working with other people on these projects together. So may as well start now. The 3-person group thing, so I've accumulated a couple of 3-person groups already because of the Arena competition. So we're getting a little tight, especially in the morning lab, close to our limit. So make sure to check with us if you're really interested in a 3-person group. Otherwise, try to shoot for a 4-person group because we're definitely safe if people go to the 4-person groups. And then that's less presentations to sit through, right? So there's a document on Canvas which tells kind of a count of roughly, I think it's up to date right now, but don't always trust it because it may be that we've approved one, we haven't updated it yet. So you definitely have to contact us ahead of time if you're interested in a 3-person group. But again, it's just simpler to go for that 4-person group. And then keep it within the section because everybody's got to present within the section. And even if somebody's willing to go to another section to present, it still means that there's more presentations. There's more people in a section, and it may be difficult for us to cram everybody into the one popular section. So just some things to keep in mind for the project moving forward. The things that you'll be responsible for there. So the first thing that's due in roughly 2 weeks. So you basically go away to. So this is between now and the precise due date is on Canvas. But the names of your team members. So you have to form a team in roughly 2 weeks or something, 2.5 weeks from now. And there's an assignment on Canvas that it's like an online quiz that you'll go into, and you basically put in the names of all 4 members in your group, including yours. And everyone in your group does that. And then I'll go through and make sure everybody agrees on who's in their group. And then I'll create groups inside Canvas so that every other assignment is a group assignment that only one person has to upload. And then your first group assignment will be this input modeling report, which is in roughly 4 weeks from now. And that's the one where you're going to actually go out and you're going to give us a very brief, paragraph introduction to the system that you have identified and the problems that you're interested in studying. And then you're going to tell us, and the precise description of this report is online. Basically, these are some data that we took on the system on the inputs. Here are some models that we fit that we're going to use in our Arena model when we finally build our Arena model. And maybe here's some output data that we've taken that we'll use for validation. So you're not going to actually do any coding for Arena here, but you're just going to be analyzing data that you've gathered. If you're doing the Arena competition, then this will be based on the data they've given you, which you should have by then. Like I said, groups will be created in Canvas. Then after those two deliverables, there's a big lull, and the last week of classes, so before finals week, then you'll do your presentations in your lab section. And then the Saturday of that, so hopefully there's enough time for us to give us quick feedback on your presentation, so then you can submit your final report on that Saturday that kind of is just after the last week of classes and just before finals week. And so that's it. So those are the 4 major deliverables: the names of the team members, the input modeling report, your actual oral presentation. So that's, you don't necessarily turn anything in for that, but you'll get evaluated on that evaluation form, and then your written report. So are there, okay, and then, so on the presentation, it's going to be roughly a 14-minute presentation. You'll shoot for 10 minutes. You can put in it, arena animations if you'd like, slides, other visualizations, whatever you think helps as a prop. Then leave a couple of minutes for questions, and then you have this 1 minute, for transition between groups. And so that's where we get the 14. It's always good on a presentation to go under, never over, because you never want to be cut off, and you will sort of get cut off for timing. And if you've got a nice, compact, and complete story that you can fit into 8 minutes, then that's fine. I'm not going to penalize you for going under 10, but you just want to make sure it's complete. Then, like I said, there's a written report, which the specific format is online, but the main content is only 4 pages long. And when you start pasting in your arena stuff, you find that 4 pages goes very quickly. There is an appendix you can add if you want to put in other things, but the actual stuff that is mainly going to be looked at is only these 4 pages. So that's kind of everything moving forward. So make sure you start forming your teams. Again, try to look for 4 people in your lab section. This assignment is online, so if you already know who you're planning to team up with, go ahead and fill this out. And it's not asking about the system; it's just asking about who you want in your team. And then you may end up finding that you have to use your book to learn a little bit more about Arena than we'll show you in class. And so in a lab, we only have a finite amount of time, so we pick things we think will be popular elements that you'll use, but there's still some things that some people's systems might be better suited for than others, and so that the index in the back of the book and the table of contents in the front can be very useful. Of course, you can also ask us, and we can point you to spots in the book for extra reference. But you may have to learn more about Arena than you're learning in the lab in order to get every sort of nuance coded in your model. So are there any questions about any of that stuff? Yeah?
Will the next 3 labs differ at all for groups that are doing the Arena competition?
Oh, the labs are still sort of an individual experience, and so they aren't catered to the project. But like I mentioned, the next lab, Lab 8, what we always do is we give you a bunch of data sets, and we give you instructions on how to use the input modeling tool, and then you'll model those data sets that we give you. So they'll be our data sets. And so the input modeling report will differ, than that'll be your data sets that you'll have to gather from somewhere. Any other questions about schedule moving forward? Yeah, I'm sorry.
Do we know who is in our labs?
Well, I mean, you can go to the lab, of course, and you can see who's there, or you can post a message. And I know not everybody, I mean, that's a serious question, is not everybody goes to lab because they're putting them online. I also recommend, you can use the discussion forums. I think you can actually, I haven't seen what the student side looks like, but I think you can actually post to just a section. So you can post to just your section as well as the whole class. But you may need to do some legwork, but to use the online forums to group together. Everybody's in the same boat, so I hope everybody is looking for everybody else. But I would definitely recommend, and it worked on already. There's been a post on the discussion forums for the arena competition, and that led to a group forming together. And so, use Canvas as much as you can. If you're really having trouble, make sure, don't let me know you're having trouble the day before the names are due. Because I'm going to say, well, but I mean, because the worst comes to worst, what will happen is if you don't have a lab, you might end up being assigned to a team just in order to make the numbers work. And so I'd like to avoid having to force people to join teams. So if you can, use Canvas or other communication means to find each other. All right, any other questions? Assignments moving forward. So there is a Canvas activity. Again, So I put a lot of these up here, but I don't, in case you did miss the, the memo, 7 of these get dropped. So, you only end up having to do like 5 through the semester. So, if I don't want you to feel like these are overbearing. These are just meant to be there to be helpful if you like to do work as we're going. And so the next one that's available is this G3 activity, which is going to be an input modeling based one. And then we've got H, J1, J3, and L. And then the last Canvas activity will be a final review one, which will be N. So these are the ones that are sort of just based on new content, G3 and these. The next homework, so there's only this homework and one more. And so this is homework G3. It's already available. I'll get the next one out soon once I make some edits to it. It is due a week after G3, but this is G1. So given that there's going to be the midterm retake, then G2, then G3, there's a decent amount of time until this is due. And then over fall break, think about your teams, think about your final projects, and what systems you would like to model. So any other questions? Or move on to new stuff? Okay. All right, so, where we left off, we were really sort of into this inverse transform sampling stuff. Hopefully we're all sort of feeling familiar with this, or if not, you kind of know how to prep yourself for the retake. Now, just to kind of get us back in that mode, imagine if I had a trapezoidal looking PDF like this one, then, described by this PDF over here, then the process that we go through, depicted graphically here, which might be more helpful for some people, is that forming the CDF means starting with the lowest point in the range and integrating up to the argument of the CDF. So if the argument is under this corner, then it's just taking the integral underneath this ramp, taking the integral underneath a triangle. And that's what you just get here, the area underneath the triangle, where it's 1/2 base times height. And then eventually, so then for this segment down here, then this is our CDF. And so to get the according segment of the inverse CDF, we just set R equal to this thing, and then solve, and we get X equals square root of 2R, where we chose the plus because all our X outcomes were positive. And then that is going to tell us that from 0 to 1, we're going to have R values from 0 to 0.5. So that basically means if our random number generator drew a number between 0 and 0.5, we would plug into this formula here. Question?
Yeah, but for like the inverse transform, like the trapezoid, it would have to stop at 1 because it stops being a function at x equals 1 if you take the inverse, right?
So we end up at 1, you go to the sort of a different branch, and so that's what I'll sort of get to here. But the CDF is the area underneath this curve, and the area underneath this curve is always invertible, even if the PDF is not invertible. So it's true that the PDF here is not invertible because at 1 it has a lot of values here, but the CDF, because you're integrating under that, will always be invertible. So the CDF is always going to be, you at least graphically will be able to flip it, even if you don't know the analytical expression. So you've handled from 0 to 1, and then now, if you imagine, I'm trying to take the area underneath this thing. Once I hit 1, the story changes a bit, and I have all of this triangle just there as a constant. And now I'm integrating this tiny little rectangle. And so that's what we see down here, is that you see that the integral now in this range has got this blue 1/2, which is just all of this area, plus the area of a rectangle, which in this case is just the width times the height. And so that's why it ends up just being this t, which is like the height is a 1 and the width is t, where t is this tiny little region here. And I'm integrating from x to 1, and that's where I get these limits of integration. So I end up landing with a CDF for this region that is just x minus 1/2. And so I can then invert that little region by setting x minus 1/2 equal to r. And then that gives me this, well, okay, so x is equal to this, r plus 1/2. So for the upper region, for when r is greater than 0.5, we use this formula to get our outcomes, not the other formula. So I take those two things together, and I get this inverse transform. It's got this top part for r less than 0.5 and this bottom part for r greater than 0.5. And then I can implement that in a bunch of different ways. So, you can implement it in Excel, where I could use, in one column, I could generate a random number. In the second column, I basically implement this, where I say, is the cell in the previous column less than 0.5? If so, take the square root of 2 times it. Otherwise, add 0.5 to it. And so that ends up giving me, my outcomes. And so these are my uniformly, in column A will be my UO1s, and column B will be my outcomes from the trapezoid. And then I just fill that thing down to get as many samples as I want, and then I can take a histogram. Now, before Excel had its nice sort of histogram features built in, there was kind of a long way to do it, and if you're interested in that, that's what you're doing, these sort of steps here. But now there's a graph type right inside Excel, so you usually don't have to worry about manually doing it. But if you wanted to manually build your own histogram in Excel using the frequency command, then you could do that. And I'm going to skip by that, but just know they're here. For some reason you're ever stuck using a legacy version of Excel, there is this command frequency, but it is an array function. So if you've never used array functions in Excel, you have to Control, Shift, and Enter to make them work, not just Enter. They're just a little weirder than your normal Excel functions, but in the end you get a nice histogram just like we were expecting. If you're in a MATLAB type program, you might do similar sort of scripting where I say I could generate a vector of uniformly distributed random numbers between 0 and 1, and then I generate a vector of my samples where for all of the numbers that I drew that were between 0 and 1 that are less than 0.5, I take their square root, and for all the numbers that were greater than 0.5, I add 0.5 to them. And then I end up getting a new vector of samples that I can use a command like hist or histogram, and then there you get a histogram in MATLAB, so same thing. How do I do it in Arena? Well, there's a bunch of different ways to do it in Arena. This is a little bit of a contrived example, but you can imagine having entities coming in and getting created. Maybe each entity is then assigned what I'm calling a trapezoidal delay, and then they're delayed by that trapezoidal delay and then disposed of. And so what would I do in that assigned trap delay? Well, in both of these examples, Excel and MATLAB, I generated my random number samples first from 0 to 1, and then I used them to generate my trapezoidal. In the assign block, you can put multiple assignments, and they get executed from top to bottom. And so in this top one, I assigned R to the RA expression, which does the draw from 0 to 1. And then in the next one, I use this expression here, which is a way to combine these two cases. When R is less than 0.5, it takes the square root, and then it has a little plus here, and then when R is greater than 0.5, it adds 0.5 to R. And if I do that, now that you've seen in Lab 7, there are these visualizations. Well, there is a histogram visualization inside Arena, and I can actually say, show me a histogram of trap delay, and as the simulation will run, it will collect all of the trap delays that were generated and show you a histogram. And it's not a great visualization, it's just meant to kind of spot check things. You wouldn't put this in a report, but you can see it also is that nice trapezoidal shape. So this is how you implement that in multiple ways, all roughly the same. So, and then likewise, if you need another example, I'm not going to go through this in detail, but just know it's on the slides. Here's the trapezoid going the other direction. So if you're studying for the retake, if you just want to see another one of these, I've got gone through the example here where I've generated the CDF and inverted the CDF, and then I've also implemented it. In this case, I only did it in MATLAB because I'm hoping the formula is easy enough to see, and you can see it gives you the trapezoid in the other direction as expected. So that's where we've been so far. We can do all of that. But the real sort of question now moving forward is, let's say we took data like this to begin with. How can we then say with any certainty that this is the PDF that we want to represent that data? So you go to the Chipotle example and you end up getting this for some service time distribution or whatever you've got, and you say, well, that looks kind of trapezoidal, but it's also a little noisy. How do I know it's not just a bad luck on a triangular distribution or bad luck on a uniform distribution? Or maybe this is actually normally distributed and maybe I truncated it by accident when I was taking my data. So those are the questions that we have to deal with now. how do we rigorously compare this hypothetical distribution to these real data? And you know, the thing is, already we kind of know how to do that. So already we've done this before the midterm, but we did it for this special case. And so these are uniformly distributed random numbers between 0 and 1, and we use the Kolmogorov-Smirnov test and the chi-squared test to check whether these were sufficiently uniformly distributed. And so we basically were saying, do these data, are they consistent with this hypothesis? And we are going to take those two methods, among other things, and generalize them so that taking the same stuff that you knew how to do before the midterm and apply it to this example, which the math looks almost identical, but the application is just slightly different. So that's one of the little things we're going to do moving forward. And then the more exotic thing that we're going to do, or we're going to add to that, is then to say, well, then how do we pick between this one and this one? So how do we even come up with these hypotheses to begin with? And so that's going to be sort of where we're starting here in this input modeling exercise. So that's kind of motivation for what's moving forward in this Unit G in input modeling. Are there any questions about that? Most of that was just review, getting you ready, for the retake, inverse transform, keeping it up there over fall break, and then motivating what's going on moving forward. Questions? People feel pretty clear. I think you saw in the midterm, I didn't ask you to do a lot of sophisticated math, but I wanted to really test whether you had the concepts down of this inverse transform method applied in both the discrete case and the continuous case. So, and again, I would sort of focus on that. All right, so, moving forward, input modeling. Imagine you've got an arena model like this one. This is a really, really simple model of an airport screening process. So we've got passengers that arrive, their identification gets checked, they might pass security, or they might get denied. And so we have all these questions that we can build this. This is easy. You just drag these blocks in. Then the hard part happens. So this is the thing that's most conspicuous about ARENA. You see these block diagrams, but the real work goes into what goes on inside those block diagrams. So for this one, how do we model the time between the arrivals? So I use this as a motivating example. Before the midterm, passengers are arriving with these variable times between them. How do I choose the distribution to put inside here? Do I choose an exponential, for example? So I might decide that I want to choose this exponential here. Maybe I take all of their inter-arrival data, I put it in a histogram, and I look at that and it tells me, oh, this looks pretty much like an exponential. I'm going to use an exponential with a mean that matches the mean from my data. It kind of makes sense from a heuristic point of view, but how can we make that a little more rigorous? Once we've got that, we can go into ARENA and implement that. So I can go into the create block and I can say I want an exponential, I want this mean. So we can see here, at least there is a path from data directly into ARENA. Roughly, I took a histogram, I took some numerical stats on that histogram, the mean of the data, I came up with a family, I ended up putting those stats into the family, and now I can simulate that. And so that's where we're, hopefully trying to go with this. But, did I make a good choice? Because keep in mind that the variation we see on the output in the reports in ARENA, that ARENA is a deterministic program. Any computer program is a deterministic program. The variation you see here is generated from the variation you put on the input. So if you chose a bad input, if you chose a poor fitting variation for the input here, you may still get variation on the output. And there may be interesting things you can say about the output, but if your input models were bad, anything you can say about the output will also be bad. So in simulation, and then plenty of other things, we call this the GIBO, or the GIGO, the GIGO problem. Garbage in, garbage out. Is that regardless of how nice the system looks, this system, you can sell this block diagram. You can say, this block diagram captures the process of what goes on at the airport. And you can put a lot of effort into making it match that perfectly. But if you have really terrible input models inside each one of these blocks, then any results that you get out of here Like your results might say, look, if you add another document checker at this particular location, it's really going to improve throughput. But if your arrival distributions were all, deterministic, then any results you get out here may be totally different once you add that variation back in. That's what I was hoping you'd see when you did the lab, where I asked you to sort of, here's a very simple 4-block model, create 2 processes in a dispose, and I said, try these with 2 deterministic, try these with a deterministic and a stochastic, 2 stochastics. What I was hoping you'd see in your discussion is that results that worked really well when things were all deterministic might have been totally different when they went stochastic, even though the stochastic averages were identical to the deterministic. So adding the variation is going to change the outputs, and adding the right variation is going to make all the difference on the right outputs. Question?
Yes, and then the statistics part prior to the simulation would be pretty much like done by hand, or like you see any other program like Retake or.
Yeah, you would use stats programs for the input modeling. We're going to show you a program called the Input Analyzer, which comes with Arena, that'll help you with this fitting process. Yeah.
I don't really get why conceptually the statistical models are the inputs and not the entities.
That's a good question. So the question is, why do we call the statistical models the inputs and not the entities? And I guess semantically, what we think of as the entities are almost like a functional part of the model. It's almost like I almost picture these things like fountains that recycle their water. And so, the entities are flowing in, they get, they move downhill in the fountain, they hit the bottom of the fountain, and then they get pumped back up. But the fountain itself is sort of, the water is self-contained inside the fountain. And so even though we think of the entities as coming in these create blocks, really where they come in and how they come in is also a question of interest to us. So I would say an input is everything that kind of needs to be put into our understanding of how the system works. And the entities are kind of already there. We already know where the entities go in. And so the question, like what's left over, and that's how do we parameterize how the entities come in. In the fountain example, how much pressure do we put into the fountain to make sure how high it goes, or what pattern it does, and those sorts of things. And that's kind of what we're doing here. So just traditionally, we refer to the statistical models as the inputs of these systems, even though maybe colloquially or just recreationally or casually, we might refer to the entities as an input. The kind of the field, as a large part, formally calls the statistical models the inputs. Does that make sense? It's a semantics thing. All right, so the model structure, this is kind of the takeaway of this intro here. The model structure may be correct, but the outputs are only good as the inputs. And so there's this Dilbert cartoon, which kind of shows this in a different context, where I did the analysis using your bad assumptions, those are bad inputs. Then I applied your flawed logic and arrived at your predetermined answer. And shall I begin disillusioning the team? This needs a pie chart. And so the idea here is that I could go back and engineer. I could take this same system here, and I can engineer inputs to make my operational change look like it performs a lot better, because I'll have found the perfect inputs that only work for the change that I suggested. And then I can show you outputs, and they might be very convincing. But if I don't also show you my input assumptions, then you don't realize that actually I've stacked the deck. And so this is kind of the science of stacking the deck in an industrial scale. So we don't want to stack the deck, because we want to be honest modelers. All right, so input modeling is all about selecting probabilistic models that mimic these variations. Random variables are our inputs, not the entities themselves. Examples that hopefully these feel, I think everybody, when I asked these concepts on the midterms, was doing a pretty good job. When I asked, when the matching case, when it came down to the individual one where I think I gave, at least on, I think I gave examples inside an airport actually, then it got a little hairier, but I think still people feel like they're pretty much understanding these things. But these examples in queuing systems, the inter-arrival times and the service times, those are our inputs. In supply chain models, they're typically the demand, like that's a discrete, like how much demand I get each day, and the lead time, how much delay it takes for me to order new supplies. In reliability problems, it might be the failure time. So these are common inputs. So the distributions of these variables model the real world, and so we want to take data on the real world and do a good job building stochastic models that capture that data. So how we're doing this is so today I'm going to talk about collecting that data, and then lecture G2, which we take after the retake, then we'll talk about how to identify the kind of family of probability distributions given the data. And then for 3 and 4, how do we actually then choose parameters for those families that we've identified and evaluate the fits. And so the part 1 of the homework G3 is all about this, where you have to evaluate the fit of a particular distribution and see how estimating a parameter versus being given a parameter changes that process. So that's kind of where we're going in this roadmap of this unit. So let's talk about collecting data. So available data is not always relevant data. So in a simulation study, let's say we wanted to study a clinic. Well, so we set the thing up. We say our entities are our patients. Our activities are maybe the time it takes for the nurse to obtain a patient history. So that sounds good. That sounds like a clinic today. That sounds like a clinic 20 years ago. That probably sounds like a clinic in 20 years. Maybe the nurse at that time will be automated, but that maybe but that's actually going to get into the guts of this example. So a prior study took data on this clinic, 2002 study. And so you've got, and I've definitely had examples like this where you talk to somebody in industry and you say to them, I need data on this aspect of your system. It would be great if you would finance a study where we could go out and take data. And those come back and they say, well, wait, we already have that data. We did finance a study like this from 2002, from whatever, 15 plus years ago, and we have data on exactly what you want. It's perfect. It's serendipitous. We don't need to finance anything. Here is the data. And so the question is, should we use it? So how many people think, well, I guess, take 30 seconds, talk amongst yourselves and think, what could be potential problems with using this data now? And you can think, in the case of a clinic.
Based on the title of the slide.
All right, let's bring it back in. So it just occurred to me that this problem might be stale in itself. So occasionally, by the way, on the Scantrons, I don't need your birthday. I think it's great, but I'm not going to remember. But occasionally when I do, it's always a stark reminder of how I'm getting older. And so I realized that I think I at least saw one 1997, and to you that's not a surprise, but to me it's always kind of a shock every day. And so I realized that maybe this example, some of you may not have remembered what it was like to go to the doctor in 2002 and how things have changed. But let's imagine. So what problems do you think could occur if I'm just focused on the time it takes for a nurse to obtain patient history, comparing 2002 to today? Any thoughts? Yeah.
Would they need to contact their doctor, and then hopefully they're open to get that information?
Would they? Well, I guess I'm saying, let's say that. Oh, don't worry about the IRB stuff or the. Let's say that this is data that's been anonymized, and it is reasonable data. That it's data that we were allowed to take in 2002, and we're continuing to be allowed to use now. So I guess I'm saying that as a collector of data, could you trust these data, and why not? And I guess the question would be, what things might have changed that could have determined the time it takes for a nurse to take your history if you go from 15 years? Yeah.
Number of patients.
Well, I mean the number of patients, but that's usually we think of as each individual patient probably has the same activity distribution, unless the number of patients have caused nurses to have to be retrained to maybe not ask as many questions. But maybe that gets into it. Maybe they ask different questions now. Yeah.
Technology.
Technology. What sort of technology?
So like now you fill in the stuff like in an iPad or like tablet.
Right. So now you do a lot of stuff yourself. Back when back in 2002, when I went to the doctor, if I went in, a nurse took my stats, she'd have a clipboard, a paper clipboard, and would write everything that I would say down. My whole history, she would write, in, I assume not long form, but I also assume not short form. But either way, it took a lot of time. Now when you go in, what do the nurses do? He or she is probably sitting at what? A desk with a computer. There were no desks and computers when I went into waiting rooms or clinics and clinics and all that. But there were tables, but there weren't desks. Like there weren't all these things that rolled around on carts with like crazy arms and things like that. Then so now everything's typed into the computers. The computers are rolled around from room to room, or they're stored in the room. That totally changes the time it takes to take this. Typing in something. You can automate a lot of stuff where they can say like it can remind the nurse what questions to ask and what the options for answers are, and they can select them all. It could be a lot faster now. And that's going to affect this activity distribution because remember, that's a duration. So anything that reduces the duration of time over a 15-year period is going to mean that these data are useless. So stale data is a bad thing to get. So that won't be that much of a problem for your final projects unless, let's say, like occasionally I'll have people and they'll hook up with their like family members and they'll say, hey, you run a big company. Do you have some data I could use? And that family member will say, oh, well, I actually do. If you look, if it's kind of old data, then this may not, that it may not actually help in the current operations. All right. So the other thing, let's say that you're studying security protocols at a metal detector feeding a government building. And your entities here, so you draw the diagram. Entities are people. The activities are the time it takes to pass through the metal detector. And so you're going to collect 1,000 observations of the time it takes people to actually walk through the metal detector. And you notice that the mean and standard deviation are nearly identical. So it's almost as if the distribution has a single parameter instead of two parameters. Can anybody think of what distributions we've talked about that are often used to model times that only have one parameter and not two? Where the mean and standard deviation are identical. I've heard one person say it. Wait for somebody else. It's a common distribution that comes up with modeling times. Only one parameter, mean and standard deviation are the same. And it's continuous, so it can't be Poisson, but it's related. Exponential. So you might say that you see this on its own. You say the mean and standard deviation are identical, and it's modeling times. Got to be an exponential. So following the experience that I kind of said a couple slides ago, I'm going to just take an exponential and match up the mean. But then I look at the mean, and it says the mean passage time is 30 seconds. Does it take 30 seconds to walk through a metal? I'm not talking about lining up. I'm not talking about taking your stuff out. Just walking through a metal detector. Walking 3 feet. Does it take 30 seconds to do that? Probably not. So this probably indicates that an exponential with a 30-second mean is not going to be a good choice. And it probably means that this coincidence of the mean and standard deviation being the same was probably just a coincidence. And we need to look more closely at the data. So closer investigation shows the distribution is bimodal. It has two peaks. And so this 30 seconds is firmly within those two peaks. So there are long times when the metal detector is triggered and short times otherwise. And so the idea here is that if you just tagged somebody with the time they entered the metal detector and then waited for the time where they exited the security system, then those who walked right through the metal detector would get short times. But occasionally someone will get flagged. They'll go back around, get rechecked, and then they might get sent back through the metal detector. Or maybe they just got rechecked and they got sent along the way. But if you were only keeping track of when they entered and when they left the whole system, when they entered the metal detector and when they left the system, then you're going to get two groups of people. those that get flagged and those that don't, and the data will show 2 humps. And if you just average across them, an exponential is not bimodal. So we need to somehow be able to create something that has those 2 humps. And we have not seen any distributions in our catalog that are bimodal. So we're going to need to do something special for that. Are there questions about that? Does this make sense? What I mean by a bimodal distribution in times. This can definitely happen when you're taking data for your final project, where if you're not paying attention to all of the details that are going on when someone, let's say, is ordering their burrito, you might find that there's some people, when they order coffee, for example, let's say they go to Starbucks and they order a coffee. Some people, they come out and they get their coffee immediately. The others have to wait for, could be 5 minutes to get their coffee. What's the difference there? It might be the difference between a drip coffee and an espresso-based drink. And if you just are paying attention to when they got their drink, you would end up thinking that you'd average all those together. But if you look at the whole distribution, you'll get a bimodal distribution. And you'll have to say, I need to know who's going to order a drip coffee and who's going to order an espresso drink. And then once I know that, then maybe I can have a simpler model. All right. Yeah. Is there a question? Sorry.
Yeah. So what would you do in a situation where there's it's so customizable that you have more than one piece?
Yeah. So we're actually going to.
More than 2 pieces. Sorry.
We will work an example, I think either in lecture G2 or G3, where I actually drill down on this metal detector example and actually build up an arena model which simulates that, and I add multiple peaks and show how you could possibly make that work. Yeah.
And you said that the mean is always going to be between the peaks, right? Like between the modes.
Well, in this particular case, I was just saying picture it being in between the modes. I guess it doesn't have to be, but very often when things are bimodal, it just kind of depends on how high the modes are, but the mean's probably going to be in the middle.
Okay. And is it kind of like generalized?
Well, I mean, so remember, mean is a balance point. And so if you have a pile of sand that happens to be piled up on a board like this, then you have to ask, like if I was going to put a fulcrum underneath there, where would the pile of sand balance? And that's the mean. And so if this is really big, then that means I'm probably going to be shifting and the mean's going to be quite, in here. But if both of these are equally high, then the mean's going to be in between them. Okay. All right, so security protocols. So we're going to make a revision. This is kind of getting at this idea of what, how do we deal with this? So our revision is we update our model. So here we basically indicated that when I had one service time, I could not model it as a single exponential. And I don't have any bimodal service times in my catalog of things that I know how to simulate. So I am going to throw away this model and adjust the model structure. So now I have 3 distinct input models. I have long passage times that I have to model. I have short passage times that I have to model. And I have a probability of which one you get. So now every entity is going to go in, and then that entity is going to be either going to be sent off into one distribution or the other. So, so this right here, and I'll show, and it will work again, an example of this in one of the future lectures here in this unit, where we'll actually show how to build this in Arena. But I'm hoping you're at least picturing it, as a decide block with going up to one process block that has a long time, or another process block that has a short time. And so that's one way I could end up then fitting only the long passage times, and maybe that is exponential, and only the short passage times, and maybe that is exponential. And now I fit 2 exponentials, and I get my bimodality because I had to, split them off into 2. But that means now I also need to gather data on how frequently people trigger the detector. So you might be in a building where you get a lot of people that don't know how to use the metal detector, and they're constantly triggering it. Then this is going to be a very high probability. Or you might be in a building where only people who work there come in, so everybody knows how to use the system, so this would be a very low probability. And so you'd have to keep track of how often the metal detector gets triggered versus not to calculate that. So then, further inspection of this, and we see that some passage times are negative. Well, that doesn't make any sense whatsoever. How did that happen? So we have now to decide what to do with these data. Can we fix them? Can we say that, oh, actually we did some automated process of calculating, and occasionally due to some numerical issues, we would accidentally subtract when numbers were close together and we get the order wrong. And so negative numbers, they're implicitly 0. I can just replace them with 0. Maybe I can do that. Or if they're just garbage data, like maybe that, somebody accidentally put a row in that was incorrect, or there was some corruption or something like that, maybe I can throw them out. So I have to make these decisions, and these are very subjective decisions. Sometimes I might have to compare alternatives. If I make them all zeros, how does it change things? If I throw them out, how does it change things? If I get the same fit, regardless of whether these data are turned into a 0 or thrown out, there might be so few of them that they don't matter. So maybe I just throw them out to be safe and it's not going to hurt anything. But if these are my only data, then maybe it's going to hurt to throw them out, and I need to sort of think, is there anything else I can do with these data? And this will happen where you'll get, mistakes. There might just be somebody entered things in wrong in the spreadsheet. They transposed 2 numbers. They typed into one cell incorrect from another cell. And so, that's going to happen. And you need to make sure of that because, negative values, you have to be careful. I've seen people present, at their final projects, and they show me a histogram of data that they've taken. And there will be this funny couple of outliers that are negative, but this will be in like a service time distribution. And I'll ask, like, well, what's going on over here? And they'll say, well, we just didn't know what to do with those. But that's not really an acceptable answer. Like, you don't ever, what you're saying is you're okay with simulating negative passage times. And that's just not a good simulation. That's garbage in. So figuring out what to do, that's going to be more of a subjective thing. Hopefully you'll build up some intuition as we go through examples during this unit, but some of this, you just kind of learn on a case-by-case basis on what the right thing to do. All right, so what heuristics should you build up as you start taking data here? So I've got a couple of data examples here. It's basically just a couple of different steps, and then we'll be done mostly for the day. But I do, if we have time, want to add on a couple of comments about Lab 7 that may help as you're going through Lab 7 in completing the report. So pre-observation and planning. So don't just go out. So once you've identified your project group and your system, then think ahead of time about what sort of things you could take data on. So pre-observation, like let's say you want to model a coffee shop. A lot of people model coffee shops, and so we always encourage you not to model coffee shops because we get like tons of coffee shops. But if you do model a coffee shop, model something novel and interesting about that coffee shop. So not everybody's the same, but it's okay if we get a lot of coffee shops. We can compare them to each other. But let's say you go to a coffee shop. Sit there for a while without taking data and think about all of the different things that you might want to measure. Maybe there's some special idiosyncrasy about the way the queuing system is set up that requires you to count the space and say, you know what? If you can't fit more than 15 people in line here, maybe we need to take that data down. Or maybe you notice a transfer time. The door is on one side. In order to get into the queue, you have to walk all the way across the restaurant. And maybe when the restaurant's busy, that time takes a different amount of time than another time. So think of all of these weird things, all these different ways you could take data and plan that out. And then come up with kind of a schedule of like, what sorts of types of data that you think you want to take. And then as you're gathering that data, don't wait until the end of your study to see that you didn't gather enough data or you gathered the wrong data. So it's hard to sort of know if you gathered enough data when you haven't gathered that much data to begin with. You kind of know you always need more data. But you can still say, is this adequate? Is this giving us consistent results? Is this, if we collected more of these data, would I actually be able to fit this distribution? Is there something going wrong with the data? Am I getting a bunch of negatives where I shouldn't be negatives? Do I need change to be made? So don't just collect a bunch of data and then hope that it'll work out later. Look at it as you're collecting it. So this is a little more technical. Check for homogeneity and combine, or the term we use is pool, homogeneous data sets together. What I mean by that is, let's say you go to a bank and the question is, is every Monday and Tuesday different, like from each other? Like, is there a unique Monday bank distribution that's different than the Tuesday bank distribution? If you notice that when you fit data to the Monday distribution, it's roughly the same as when you fit to the Tuesday distribution, then maybe you can pool these together into just a weekday distribution. and that will give you more data, which will give you a better fit. So in these cases, don't build separate models when you can combine into a simpler model. Maybe the weekend model is very different. Question?
Yeah, so for part 2, but wouldn't that interfere though, like with your ability to like control the data, like well, it's being collected? For example, let's say that you like need to like keep up with your procedure collecting data, and if you're analyzing it, just kind of like interferes.
What I mean by that is like, you go out, you measure data on one day, and then that night you sort of take a look at the data. Like I know a bunch of people that when they collect data, that they just maybe on principle they'll collect like a month's worth of data and then look at the data. I'm saying maybe start after a week, take a look at your data and just reflect on whether you're getting the numbers you're expecting. The other example that's going to be more relevant here is that a lot of people will want to pool and they shouldn't pool. So for example, should you be taking an arrival rate per hour? And so we'll talk about this more in Lab 8. But you could say that that at noon you're going to get a certain arrival rate. At 1 p.m. you'll get a certain arrival rate. Do I really need an every hour resolution? I probably can't pool everything together and have one arrival rate per day. There's probably not a Monday arrival rate because there's going to be busy periods of Monday and light periods of Monday. But maybe I have a busy and a slow. So maybe certain times of day is busy, the other time slow. Or maybe I have a morning, afternoon, and evening. And so that gives you more data without causing you to be overly general and try to make a single daily arrival rate. Because any systems that you guys are going to be doing, you almost always are not going to be able to generalize across a whole day because just there's always daily fluctuations in these systems. But you probably don't need hour by hour, maybe every 2 hours, maybe every 3 hours. So that's what I mean by homogeneity is that if you take two small sample sets like hour, where you only have a little bit of data, if you do a crude fitting of those and it looks just like the crude fitting of the others, maybe within confidence intervals, then maybe it's okay to pool them together. And if you pool them together and they look even more like the same thing they looked like before, then maybe you can leave them pooled together and just call it an afternoon or something like that. So that's one big fix. The other problem people have is you have to be aware of data censoring. So what I mean by that is if you're waiting for something to happen and it doesn't happen before you stop waiting for it. So you might say that because you've never witnessed a light bulb failing in this room, light bulbs never fail. Because according to your data, you never witnessed a failure. But it might just be that their failure times, their durations until failure are so long, it's very unlikely that you're going to actually witness one. So you have to be at least aware of this. There are more sophisticated ways of dealing with this. There's something called survival analysis that you'll see in a little more upper level stats classes. But for now, for your project, you may just need to do some hand tuning to account for this to say, does it really make sense that my arrival time distribution, did I accidentally bias a certain distribution one way or another just because I didn't wait long enough to witness the event? So more sort of actually data here. So look for relationships between your variables. So far in this class, pre-midterm, we've been the left side of the screen. I've got inter-arrival times, and I just picked the distribution, and service times, and I picked the distribution here. So what you're seeing here are the marginal distributions of a joint distribution. So up here, this is a joint distribution of inter-arrivals and service times together. I can marginalize just by squeezing all these points down and taking a histogram of only service times. I can marginalize just by taking a histogram of only inter-arrival times. And when I look at this cloud, there's no pattern. And so this means that these are independent of these. So your inter-arrival time doesn't give you any predictive ability about your service time. But in reality, you'll find that if you measure data, you'll get clouds that look like these when you plot them together. So every point here is like this individual came in and had a particular inter-arrival time, and then later they went in, they ordered something, and it took this long for their service. And so for some reason, there's a correlation that those that arrive very shortly after others tend to also have very small service times, and those that arrive very long after others tend to have very long service times. Notice that the marginal distributions are identical. So if you just fit these, like you could fit an input model to this and an input model to this, and you would be the same in these two cases, but if you didn't account for this correlation, then you get very different outcomes. And so you might end up getting inter-arrival times that had a huge gap mapped to small service times, which apparently isn't reality in this system. And by the way, in order for me to generate these, I just generated correlated numbers here, and then I sorted one of them, and that's how I got these numbers. And so that shows how sorting gets rid of correlation. But again, look for, if you plot your data together, do you end up getting correlations between data? And if you do, you might need to build a model for that. So an example for that is, I talked about in lecture E2, or if you look in the slides, there's this method called NORDA. That's kind of the advanced way to handle that. But actually, I think what's a better way, and it's actually simpler, is to just build a little statistical regression. I can say that my service time has some slope relationship with my inter-arrival time, plus some noise. And then if I model this slope, and if I model the residual noise, then I have something that I can model inside ARENA. So inside ARENA, I can then draw a service time distribution or draw an inter-arrival time. And then from that inter-arrival time, I can multiply by 2.5 and add some noise and use that as my service time. So it's actually not too difficult to build correlations in, but you had to know to look for them to begin with in order to build these models. And if you can do this, it actually simplifies the modeling process because I have less models to worry about because service time gets set by inter-arrival time. Other questions about this correlation idea? All right, the other thing that you should look for is autocorrelation, so independence. So whereas in the previous example, I plotted two variables against each other, in this example, I've got one long series of, let's say, inter-arrival times, and I've plotted them, so this is my data here. So this data goes from sample 1 to sample 1,000. And that data just oscillates, they're independent samples, and so there's no pattern here. And how that's reflected is if I take, let's say I take 400 of these, and I then say for those 400, I am then going to then ask, I'll generate one sequence of these 400, and then I'll move ahead 10 samples. So I go from 10 to 410. And I'm then going to plot 0 to 400 against 10 to 410. And then I would end up getting this cloud here. And what this tells me is that the sample that I got 10 samples ago gives me no information about the sample I get now. The marginals are the same for the two, and there's no pattern here. And if I do that for not just 10, but every single one of these lags, and I plot the correlation, so you can calculate a correlation like this, and here it's like almost 0. I get one of those correlellograms that I talked about with autocorrelation, where the only thing that's appreciable is the 0 lag, where you can only predict yourself. Everything else is buried in the noise. And this is what we call white noise. Question?
Yeah, so if the marginals are the same, then that means independence.
No, the marginals, because in this next example, these marginals are the same. It's the correlation that represents, so if the correlation is 0, so here, if you use linear regression, you can calculate correlation, and I can calculate the correlation between these two variables is 0. Because there's no correlation between a present value and any future value, regardless of how far in the future I look, then I say there's 0 correlation, there's 0 autocorrelation, and these are independent samples. But I could do the same experiment with these data. So here's data here from sample 1 to sample 1,000, and you see it's got a little bit of a drift to it. And what this drift basically says is if I know where this point is, I know roughly where points after it are. I don't know where they are way out here, but I do know shortly after that. And so if I now do that same plot where I've got the sample now versus the sample 10 samples later, I now get a cloud that's sort of shaped like a cigar. And the slope of that cigar tells me information about the correlation between these two time points, the autocorrelation, the correlation with self. And I can plot those not just for time 10, but for time 0 all the way through, let's say, 1,000. and I get this so-called parallelogram, and I see that it's not only 1 right at 0, but it actually stays appreciably high for for several samples, and then it gets buried in the noise a little bit here, but then it actually gets appreciably large again. So this shows me that if I have information at one time period, it actually gives me a lot of information about samples in the future. And that kind of makes sense when you look at this thing. It kind of has inertia to it, where you sort of can predict where it's going to be, at least to some extent. Eventually, way out here, I lose really any predictive ability, but at least up to maybe here, I've got a lot of predictive power on maybe the next 400 samples. So that's what I mean by autocorrelation. And so if you see autocorrelation in your data, you can't just draw independent samples. You have to have them relate to each other. And so in ARENA, there are different ways you can do that. And so if you remember in Lab 6, you worked with schedules. And so schedules allow you to sort of say, we're going to draw independent arrival rates, for example, for this hour, but they're all going to have the same rate, the same average rate for this hour, but when I go to the next hour, they'll have a different rate. So by knowing the hour, you know roughly the average rate, but you don't necessarily know how one rate relates to the next rate. Or you can even build in expressions like this one, where t now in ARENA is the current time, and I can build a little oscillation, like a cosine oscillation, and then I can add a little noise to it. And this allows me to say, well, if I can draw things from this, and it will basically give me things that are, they're still noisy, but they have a trend that kind of feels like this. It has these oscillations in it. So, and there's a bunch of other things you can use. There's this thing that, again, in later stats classes you might take, you'll learn about AREMA models, or you'll see this ARMA or ARIMA, autoregressive models. And those statistical models are meant to model exactly this. But they basically boil down into things in ARENA that you can say that, like, the next price is 90% of the previous price plus some noise. This is what I mean by an autoregressive model, where the next value is some version of the previous value plus a little bit of noise. And you can build that into ARENA if you want to model like daily price fluctuations in an inventory supply problem. Then the output, so then the big thing here when you do your input modeling is just know the difference between input and output. You're going to take data, and people always on their input modeling report, I'll get a couple of groups that will say take data on queue waiting times or queue lengths, and they'll try to fit a distribution to that. You can't fit distributions to these delays because they are an output from the simulation. You can take these data, but you will then compare them to your simulation. You don't model them probabilistically. You model things like interrival times, fine-grained service times. How long does it take to make a burrito? Maybe how long does it take to do a particular part of making a burrito? You don't model the entire time you're in the restaurant because that is an output. And those outputs can be used to validate your model, but they don't go into your model, they come out. And so that's today we did this with data. We're gonna go into how you fit these things, and we'll go into more detail on how you evaluate those fits moving forward. So before, a couple of quick comments about the lab. Are there any questions about this stuff? Basically trying to encourage you to look at your data. Quick lab things, so you've got this lab 7 that you're doing. So this was the model that you're going to build in part 1, and then you're going to rebuild it using the more advanced blocks in part 2. It's an inventory supply problem, and so when you run it, you end up getting this nice up and down here. So if we have more time to kind of go through this, but the big thing that I kind of want to emphasize, because it frequently comes up, is, well, for one, I would just say it'd be good midterm retake practice to be able to answer these questions. What are the 2 types of entities? There's 2. So there's the inventory evaluator as well as the customer. One is the major state variable. In that case, it's the inventory level. One of the 4 kinds of costs, and those are listed back here on the, they're listed actually under these expressions. And then so on. But the big thing I wanted to say, because I've already seen this question come up, is if you're trying to implement this probability distribution for demand, So this is saying each time a demand comes in, it's either 1, 2, 3, or 4 with these probabilities. When you have to implement that in Arena, you have to use disk. And everybody initially wants to put these probabilities in the disk directly. But these are, disk takes cumulative probabilities. And so we saw that on the midterm, we talked about that before the midterm, and we'll use this a lot moving forward as well. That's why these probabilities increase, 0.167, 0.5, 0.833, 1.0. Yeah.
Both little s and big s are optimal pointers, right?
These are things you're optimizing. These are your decision variables.
Uh-huh.
So the little s is when you do the ordering, and the big S is what you order up to. So that's kind of the big thing that I wanted to make sure everybody saw and was reminded of, this syntax for disk. Yeah.
It's not a question, but I think there are a couple of questions posted on.
Yeah, I posted this. I see. Gotcha. On here. Got you. Thanks. So what's the difference? So the Lab 7 thing, well, I already accommodated Lab 8. So somebody wanted Lab 7 to be moved. A bunch of people weren't interested in Lab 7. But what's the difference between rand exp and exp lambda? So somebody asked, what's the difference between rand exp and exp lambda? And I guess whoever posted that, feel free to send me a note. I don't know the different contexts you're seeing this in. In things like MATLAB, the way in which you draw an exponential is through a syntax that looks kind of like this. But in Arena, the way you draw an exponential is like this, unless you use an inverse transform generator where you do like the natural log of RA times the mean, which is, but you can just use expo in Arena instead of that. So I don't quite know enough info, so follow up with me if you still need these questions answered. Otherwise, let's do an attendance question, and then you guys can get out of here. And question is, so what does GIGO stand for? So that, I heard some people say, is the submit not working?
So I actually asked the same concept. I don't have my password. Like, are you still it's the same.
I got back to you. Which one was it? I just got back to you and said, oh, it worked for us. It hasn't been working. So I can write that. So I'm on it. I know that but I'll oh, I can see it. But and it's unfortunate that the virtual lab is I don't have well, certainly the B1 is about it. Not even
Yeah, we'll wait outside.
Just raise the
yeah, just like it.
Okay.
Not in the competition, unfortunately. Competition's limited to 3. I would, yeah, but we can't. Let's talk about it.
Okay, just
Yeah. Yeah. Or else, yes, we would.
nice. Okay.
which I mean, we haven't actually gotten everything yet.
Oh, okay, okay.
Yeah, so teams of 3 undergraduate students.
And oh, right, because you guys did the same one as the final project here.
Yeah,
right?
we're
The
gonna
one-
use
okay.
that. Yeah. If we, I mean, for some reason we decide to not go through